Physics has a very stubborn rule about electricity. It never just disappears. When you pump megawatt after megawatt of power into a data center to run an artificial intelligence model, that electrical energy doesn't simply vanish into the digital ether.
It is converted almost entirely into heat. To give you a sense of scale, a modern AI server rack running at full capacity throws off roughly as much heat as a few dozen industrial space heaters, all crammed into a space the size of a large shoebox.
If you leave that rack alone in a room, it will literally cook itself. The silicon will melt, the motherboards will warp, and your multi-billion-dollar supercomputer will become a very expensive pile of toxic slag.
Welcome back to the Working Thesis. For 9 episodes, we have traced the agonizing journey of getting power from the plant to the plug. Today, we cross the threshold. We are looking at the final, unavoidable bottleneck of the AI power problem: cooling the machine. First, a quick and honest word. Everything you're about to hear is really just the two of us thinking out loud. Personal market commentary, made for learning and for fun. It isn't investment advice, and it isn't a recommendation.
And when we talk about a specific company, it's only ever to make a bigger idea click. Never a nudge to buy or to sell. So take it as a starting point for your own curiosity. Do your own research and make the call that's right for you. You can negotiate the gas turbines, you can wait 5 years for the transformers, and you can string the copper wire. But once the electron actually reaches the GPU, a completely different infrastructure challenge begins.
Inside the walls of the data center, the problem flips. It is no longer about acquiring power. It is about managing the brutal physical consequences of consuming it. The data center is essentially a massive thermodynamics equation.
And just like the broader electrical grid, the thermodynamics of the data center were never designed to handle the localized intensity of artificial intelligence. AI compute doesn't just use more power. It uses it in incredibly dense, concentrated bursts.
The final mile of the AI supply chain isn't built with logic gates or software. It is built with pumps, manifolds, refrigerants, and incredibly complex thermal engineering. If you can't remove the heat, you can't run the math.
To understand why the data center industry is currently in a state of thermal panic, we have to look at how much power is going into a single server rack. For the last 2 decades of traditional cloud computing, a standard server rack drew roughly 10 kilowatts of power.
10 kilowatts is manageable. You can cool a 10 kilowatt rack simply by blowing cold air across it. And for 20 years, that is exactly what the industry did. They built massive air conditioning units and essentially turned the data center into a giant refrigerator.
But then generative AI arrived. The processors got bigger, the memory bandwidth increased, and the power draw skyrocketed. We blew right past 10 kilowatts. Today, the cutting-edge AI server racks are drawing 100 kilowatts, and some are pushing well beyond 120 kilowatts per rack.
It is a 10x leap in power density in the span of just a few hardware generations. The infrastructure of the room did not evolve nearly as fast as the infrastructure of the silicon.
That 100 kilowatt threshold represents a hard, physical breaking point for traditional data center architecture. It marks the death of air cooling for high-performance compute.
Air is a terrible conductor of heat. Its thermal capacity is extremely low. When a rack is drawing 10 or 12 kilowatts, you can force enough chilled air over the chips to keep them from melting. But when a rack hits 100 kilowatts, air physics simply break down.
You could put a jet engine in front of the server rack, and you still wouldn't be able to push cold air over the silicon fast enough to absorb the heat. The chips will thermally throttle, slowing down their calculations to protect themselves, which defeats the entire purpose of buying a premium GPU.
So the industry had to abandon the refrigerator model. If air cannot carry the heat away, you have to use something much denser, much heavier, and much more complicated.
You have to use liquid. Water, or specialized synthetic dielectric fluids, can absorb and transport heat orders of magnitude better than air. Liquid cooling is no longer a luxury upgrade for experimental supercomputers. It is now a mandatory requirement for commercial AI.
You can see this directly in the hardware. If you look at Nvidia's newest, most advanced server systems, they're designed from the ground up to be virtually 100% liquid-cooled. There is no air-cooled fallback option for the highest-end silicon.
Liquid cooling involves routing tiny, microscopic tubes of fluid directly over the processors. The liquid absorbs the heat directly from the silicon die, carries it away to a heat exchanger, and pumps it out of the building.
It is essentially bringing the radiator from your car, miniaturizing it, and bolting it directly onto the brain of the AI. But making that transition across millions of square feet of existing data center space is a logistical nightmare.
Moving to liquid cooling isn't just about preventing fires. It is directly tied to the power constraints we have discussed all season. In a data center, you have a strict power budget.
If the local utility only gives you 100 megawatts for your building, you have to divide that up. Every megawatt you spend running massive air conditioning fans is a megawatt you cannot spend running GPUs.
Traditional air cooling is incredibly power hungry. It eats a massive slice of the power budget. Liquid cooling, while mechanically complex, requires significantly less electricity to run the pumps than it takes to run giant industrial fans.
This means that better cooling directly equals more compute. If you transition a data center from air to liquid cooling, you reclaim megawatts of power that you can immediately redirect into processing AI tokens. In a power-constrained world, thermal efficiency is compute efficiency.
Because liquid cooling is now mandatory, the companies that design and build this thermal infrastructure have suddenly become their own massive choke point in the AI supply chain.
A great example of this. And again, we use this as an illustration of the industry, not a stock recommendation, is a company like Vertiv. They specialize in the exact power distribution and thermal management systems required for the last mile of the data center.
Just like the transformer manufacturers and the gas turbine makers, companies building direct-to-chip liquid cooling manifolds and heavy-duty power distribution units are seeing their order books absolutely explode.
You can have the chips and you can have the electricity, but if you don't have the specialized plumbing to remove the heat, your data center is useless. The thermal management companies are effectively the final gatekeepers of the AI build-out.
And plumbing is the exact right word. We are taking the most pristine, moisture-averse electronic environments on Earth, and we are introducing thousands of gallons of pressurized liquid into the racks.
The engineering tolerances required to do this safely are terrifying. A single leak over a rack of GPUs could short out millions of dollars of hardware and cripple a training run that took months to coordinate.
The manifolds have to be flawless. The quick disconnect valves cannot drip a single drop. The coolant has to be filtered, pressurized, and monitored continuously. It turns the data center operator from a network engineer into a high-tech plumber.
It is a massive skill gap for the industry. You have thousands of IT professionals who have spent their careers managing Ethernet cables and software updates, suddenly having to manage fluid dynamics, pump pressure, and catastrophic leak mitigation.
This transition is particularly painful because of the legacy infrastructure. If you are building a brand new data center from scratch today, you design it around liquid cooling from day one. You reinforce the floors to handle the massive weight of the fluids, and you build the pipe channels into the concrete.
But the hyperscalers don't just want to build new data centers. They want to put AI into their existing facilities. They're trying to retrofit 100 kilowatt liquid-cooled racks into buildings that were designed 20 years ago for 10 kilowatt air-cooled racks.
You are ripping out ductwork, reinforcing ceilings, and trying to snake heavy, fluid-filled pipes through raised floors that were never meant to hold them. It is an incredibly expensive, disruptive, and slow process.
And while they are doing this, they cannot accidentally disrupt the traditional cloud services that are running right next door. They are performing open-heart surgery on the internet while the patient is still awake.
It highlights a truly bizarre sequencing in human technological development. We essentially solved how to make silicon think before we solved how to keep it cool.
We rushed forward on the algorithms, assuming the physical infrastructure of the room would somehow magically accommodate whatever the software demanded. We hit a wall of heat, and we are scrambling backward to figure out the thermodynamics.
But the thermodynamics will not yield. You cannot outcode the physical laws of heat transfer. The entire timeline of artificial intelligence over the next 5 years is intimately tethered to the manufacturing capacity of pipe fitters, pump builders, and thermal engineers. When you put it all together, the AI power problem is not a single bottleneck. It is a chain of constraints stretching from the silicon die all the way back to the power plant.
You start with the heat. To remove the heat, you need power. To deliver the power locally, you need copper. To step the power down, you need transformers and electrical steel. To bypass the grid, you need gas turbines. And to fuel the future, you need the atom.
Every single link in that chain represents hundreds of billions of dollars, years of permitting, and massive industrial heavy lifting. The digital revolution is entirely dependent on the physical world holding up its end of the bargain.
And the reality is that the physical world moves slowly. It is messy, it is litigious, and it requires concrete, not code.
But the story doesn't end here. The AI power problem is an ongoing reality. The tech industry is pouring unparalleled capital into solving these bottlenecks, and every time one link in the chain breaks, a new innovation, a new workaround, or a new mega project steps in to fix it.
We have mapped the chain as it stands today, but the industry is shifting every single week. New power plants are permitted, new cooling technologies emerge, and the scale of the compute continues to grow.
The tension between the speed of software and the limits of infrastructure is the defining story of our time. It is a story that keeps developing, and it is a chain we will continue to track. This is just the beginning. See you next time.
And that's where we'll leave it for today. Thank you, genuinely, for spending part of your day thinking this through with us.
The whole idea of this show is pretty simple. We hold a handful of theses about the world, and we test them out loud, together, a little more each day. No crystal balls, just curiosity, and a willingness to be wrong.
So, if that's your kind of thing, stick around for the next one and tell us where we're getting it wrong. Honestly, the pushback is our favorite part.
Until next time, take care of yourself and keep asking good questions.